Institute, and next, an SCI Center of Excellence for Non-Metallic Building Materials. The title of the webinar today is Innovating Reinforced Concrete Design for More Sustainable, Durable, and Intelligent Infrastructure. This webinar will be recorded as for previous IAPSE webinars. All of the recordings are available on the e-learning page, and I think Firat is going to post into the chat the link to that webpage for you. Each of the 4 panelists will speak for 20 minutes, and at the end of the webinar today, we will have 15 minutes for question and answer, and I will conduct it by the Q&A chat function in Zoom. My name is Dolores Pulido. I'm the chair of the Spanish group of IAPSE, and I have the pleasure to act as your moderator for this webinar. The webinar aims to promote innovation in concrete structure by presenting the point of view of industry, academia, and designer on how composite materials and smart engineering can provide more sustainable, cost-effective, durable, and intelligent structure. I would like to introduce in the order in which they will participate in the webinar, the 4 panelists that you can see on the screen, and summarize the content of the presentation. Professor Antonio Nani's research interests include construction material, their structural performance, and field application with a focus on the sustainability and resilience of building and civil infrastructure. During the past 35 years, Nani has studied concrete and advanced composite-based systems as the principal investigator in many research projects. His research has impacted the work of standard writing technical committees in the United States and abroad. Nani was elected president of the American Concrete Institute, ACI, and serves as the 100th president for the term 2023 to 24. He is a fellow of 4 technical societies and a registered professional engineer in Italy and 4 USA states. Nani will present how GFRP rivers have revolutionized international standards and how standardization has made possible allowing this technology go fast from North America all the way to Middle East, and how current large glove projects are looking at composite material as the only material that can allow true and constructive sustainable growth. Paolo Casadei is the business development leader for European Owners Corning Fiber, focused on enabling next generation concrete reinforced performance and the Matibar fiberglass river product. He received his Bachelor of Science degree in Civil Engineering from the University of Bologna, Italy, and holds a PhD from the Department of Civil Engineering at the University of Missouri-Rolla, USA. With over 20 years of experience, he's an expert on the use of new material in civil engineering. Currently is involved in the development, design, and application of more durable and sustainable concrete. He is an active member of the American Concrete Institute, International Federation for Structural Concrete, FEB, and other European and global associations and committees. Casadei will provide an update on composite GFRP rivers in terms of mechanical properties, advantages, application, and most importantly, the current standard for certification in Europe to guarantee quality and constancy of performance. Professor Camara, full professor of structural engineering at the University of Chieri Pescara, Italy, has been with the institution since 2004 and served as the technical director of ASDEA. He holds a master in civil engineering from the University of Bologna and a PhD from the University of Colorado at Boulder, where he was also a research and adjunct professor. With over 100 publications, his research combines experimental and numerical approaches in structural engineering. His expertise includes advanced non-linear analysis and contribution to the design, evaluation, and safety of critical infrastructure, particularly in seismic-prone regions worldwide. Camara will present how innovation in design and intelligent monitoring can really make the difference, especially for infrastructures. AI implemented in the monitoring system allows to continuously modify the FEM model with data implemented from the real structure, allowing a continuous update of the structural model and a much safer adoption of innovative material. Pedro Manocheri, senior structural engineer at Carlos Fernandez Casado since 2016, has been actively involved in the analysis, design, and supervision of diverse and notable bridge projects worldwide, focusing on research-driven solutions to structural challenges. He holds a Master of Science from Technical University of Madrid, where he is pursuing doctoral studies in earthquake engineering and structural dynamics. Manusheri plans to talk about the application's possibility of FRP bars in bridges and structure. In order not to waste time and to make the webinar run more smoothly, please each speaker at the end of his presentation gives the floor to next speaker. I'm going to hand over to Professor Nani to give his presentation. So Antonio, it's over you.
Professor Pulido, it's certainly a pleasure to be invited to this event, and I'm sharing my slides now. I will go into presentation mode. And okay, so again, thanks to you, thanks to the Spanish group of YAMSE for this privilege of being with you today. I will try to stay on time. It's 3:06 in my clock, and I will hopefully be done by 3:26. The topic that was assigned to me is to speak a little bit about the international perspective, and I will do that by touching two topics. One, the code itself, ACI 440.11-22, and then to speak about some of the field applications that I think are representative of case studies that could be useful to the audience today. So why do we use FRP? The obvious reason is we have been trying to protect the steel reinforcement in different ways. And you see them listed here: concrete cover, membranes, corrosion inhibiting admixtures, covering the bars with epoxy. But now the idea is, let's solve the problem at its origin. Let's replace the steel where it makes sense with the composite reinforcement so that the durability and longevity issues are addressed. Where are the most interesting applications of these materials? Obviously, when there is corrosion due to chlorides, also when the concrete has a low pH, and certainly in structures where the minimum concrete cover could be reduced. This is, for example, an interesting application in the precast industry. There is two other fields of application that may not be of great interest to the audience today, but is worth mentioning. The first one is where we require electromagnetic transparency, for example, in MRI type of application. Certainly when we require thermal non-conductivity, again, if we look at the precast industry, this could be of interest in the area of panels, where we want to avoid thermal bridging. And finally, in the geotechnical applications where we have the soft ties in the walls where the TBM, the tunnel boring machine, needs to start the excavation. Today, we will focus really only on one type of FRP, and in particular GFRP, glass fiber reinforced polymers. And in this particular case, we refer to two types of constituents. The first one is the fiber itself, which is ECR. So is the traditional e-glass with the formulation to be more corrosion resistant. And the resin is a vinyl ester, a thermoset that has demonstrated over the course of the years a satisfactory, more than satisfactory performance. Why the selection of these two materials in particular is because in the code that I will mention in a little while, we make reference to a material specification in ASTM, and in particular, as you see here, ASTM D7957. So the performance of GFRP bars is specified both in terms of physical and mechanical properties, and the rest of the conversation today, at least from my perspective, is related to this type of composite. The GFRP bars have been around for quite some time, I would say more than 30 years. They have been also started with e-glass, now we are at ECR. We started with the polyester, now we use vinyl esters. And the reason is because we are paying a lot of attention also to the durability. What is interesting, and you can see in the pictures on the right-hand side of my slide, is the shape of these bars. Unfortunately, we have not arrived to a standardized configuration. And so you can see different surface profiles. They could be helically wrapped, ribbed, sand coated, grooved. And the reason is obvious. We are all reinforced concrete people. We understand that there has to be a bond between the reinforcement and the concrete for the transfer of stresses. And therefore, this is a key issue. Every manufacturer does it in a slightly different way, but we have to ensure the quality of the bond, and this will be one of the test methods and limit that the ASTM D7957 provides. The test methods that are indicated in the 7957 are various, and here you can see a selection. Starting from the left-hand side, the tensile strength that gives us the ability not only to determine the capacity and tension of these materials, to the far right, where is a test that maybe civil engineers are not very familiar with, which is the enthalpy of polymerization. So these are all very important tests to determine not only the mechanical properties that are to be used by the structural engineer, but also the physical mechanical properties that guarantee the quality of the reinforcement. I report to you here, just for information, I know it's a crowded slide, two tables that appear in the D7957, just to give you an idea of the limits. For example, I read only the top one, the fiber content should be at least 70%, and so on and so forth. There is no reason you need to memorize anything that is written here, but I just wanted to let you know that this standard, this specification provides you with all you need to make sure that you're adopting the right bar if you are an end user. Just a final remark related to ASTM. The committee D30.10 that is responsible for this spec has just recently published another one, D8505, that I'm not going to cover today, but the peculiarity of that one, in particular, as far as we are concerned today, is it allows or it specifies the characteristics of bars with the modulus of elasticity of 60 GPa, as opposed to the one that you see listed here that are limited to 45 GPa. In the past, as I mentioned to you, we have been looking at this for over 30 years. There has been questions about the durability of glass fibers, particularly because of the FRC, technologies. But we have demonstrated over and over that the durability is not an issue. This slide speaks to a research project that we conducted a couple of years ago, selecting as 11 bridges. You see the dots on the map on the right-hand side that were built over a period of 15 to 20 years. We collected the cores, and then we tested the GFRP bars, and even if they were of the old generation, in other words, with e-glass and polyester, the durability was exceptionally good, and there were only minor signs of physical-chemical deterioration. So now let me switch gear very quickly to the building code. We consider this an epochal accomplishment. We published this in 2022. I know that the audience today is primarily more interest maybe in bridges and structures as well, but I think that the reference to this code is important because it's really written in mandatory language and is adopted also by IBC, the Model Code International Building Code. So as any building code, this provides minimum requirements for material design detailings of structural concrete buildings and speaks to the issue of GFRP bars that conform to the requirements of 7957. The code covers all the topics that you see listed here. I'm not going to go into the details here, but it is all that the designer, the engineer of record needs to specify and design these materials, from ultimate condition, ultimate limit state, to the serviceability limit state. I'm sure that there will be question later. Materials such as GFRP composites are linear elastic to failure. They certainly are not elastoplastic like steel, and therefore the let's say their application in seismic zone due to the ductility is an issue that needs to be addressed. And the way that we do it in ACI, but I would say not only in ACI, but the Canadian standards as well as other, is to address this from a perspective of deformability, that we define it as the ability of a member to undergo large displacement prior to failure. If one day you wish to attend a webinar where we go into the details of what this means in terms of design, I will be delighted to help you with that. The areas where you need to recognize the major differences between let's say, RC, reinforced concrete with steel, as opposed to GFRP, are listed here in yellow. Shear strength is different, the dowel action is different, the bond performance is different. The design procedures, as we mentioned, are similar, even though we need to be cognizant of the fact that the bond is different, the shear strength is different, the development length has to be different. And the other thing that you need to recognize is that the serviceability design takes a primary role also in the use of GFRP-RC, because the modulus of elasticity of these bars is about between 1/4 and 1/3 of that of steel. And this has implications, particularly on deflections. So with this, took me just about 10 minutes to finish my first topic. I want to take you through some field application. I selected 4 that I think are representative of what has been done in the last few years. Let's start with the bridge in South Florida. We're in Broward County. This bridge is certainly interesting for the items that you see in this picture, colored in pink and purple, and they are the cast-in place deck as well as the pile caps. This bridge was only built with non-ferrous materials, but I'm not going to go into the elements consisting of pre-stressed concrete with carbon FRP tendons. Here in this picture, you see the cages, so nothing different from what you do in the case of steel, other than the workers love it because of the lightweight of the material. The weight of GFRP is approximately 1/4 that of steel. I'm sure that my colleague, Dr. Casadei, will speak to the issue of constructability later on. Here you see the complete assembly of the cages, the casting completed for the pile caps. And in this picture, particularly paying attention to the right-hand side, you see the GFRP reinforcement for the continuous flat slab. This is the first case. We typically have designed bridges that were simply supported slabs or girders. In this case, it's just a continuous flat slab. This is royal we, obviously the role of the university was to complementary to that of the designer and the contractor. We conducted a load test on May 1st, 2021, before the bridge was open to traffic, to check to benchmark the stiffness of the bridge. And what we determined, we conducted a test after 1 year and after 3 years. You can see the results here. And fundamentally, what we're saying is the frequency, the natural frequencies of the bridge has not changed over the period of 3 years. So there is really no deterioration of stiffness, and therefore, even through visual inspection, we could not see cracks in the slab. The other field application is also in Florida. This is published in CI International. Is a seawall made of secant piles. Very exciting project. You see a picture here on the right-hand side of the job, almost completed. The reason this is very important to us and the people in Florida, Look what happens to Flagler Beach when the hurricanes come. And A1A, the highway that you see here with all the traffic on the left-hand side, is an evacuation route. So it's very important to have it functioning after an event or even before an event, sorry. So these are the secant piles. Approximately 5,000 foot of seawall was built. At that time, this was the largest GFRP project in the country, over 1.5 million linear feet of GFRP bars. If you want them in meters, just divide it by 3 and you get a sense of the length of the bars. These are the cages being built at a very fast speed. I could tell you much more in terms of productivity, but today we don't have the time. Very intelligent contractor that prepare a guide form before the drilling of the piles. And here is the execution. The cages were delivered to the site, and then eventually they were installed. Approximately 1,800 plus piles were installed over these 5,000 linear foot of seawall. There were concerns about the potential proper sinking of the cages. We had no problem, and actually our recommendation in the future is to avoid the nose that only complicates construction, but really doesn't serve any purpose. I would like you to pay attention to this picture now, especially on the right-hand side. This was immediately after the completion of the seawall. And you see that you don't see the seawall, obviously it's covered with sand and it's very nice and pretty, great environment. But guess what happened after 3 years? The job was completed in the summer of 2019. In fall 2022, Hurricane Ian just decided to touch that area, and look how the wall resisted. Extremely excellent design, and there was no impact on A1A nor the inhabitants. The next project takes us to the Middle East, in particular Saudi Arabia. This is also published in Concrete International. This is a largest concrete structures, at least at that time. It was completed in Saudi Arabia in 2021. Is a flood mitigation channel around the city of Jazan. Is a city that was just being built. You can see the red line here on the right-hand side that protects the city from floods. Jazan is just at the border between Saudi Arabia and Yemen. Some pictures to give you the magnitude of this job, extremely interesting. The pictures explain the situation themselves. I don't have to get into the details. Look at also the working conditions and imagine the day temperatures in this part of the world. The canal was designed with epoxy coated steel, and eventually the owner decided to switch over to GFRP rebars. Casting was done mainly at night because of the temperature. Not only is to more convenient for the workers, but also for the curing of the concrete, avoiding shrinkage cracking. This slide is only to let's say, give you an idea of the cost. There were 21% savings compared to the use of epoxy coated rebars. Unfortunately, we don't have the time to go into the details, but the point that I want to make is very simple. The cost of a GFRP structure not necessarily would exceed the one of conventional steel. The last item I want to mention very briefly is almost like a project that is in this experimental stage, but I want to tie to the sustainability issue that is obviously very dear to you all and myself in particular. This is a project, is a what we call an eco reef. We are just outside Miami Beach. You can see the location here in the left-hand side picture. These elements are called sea hives, but the point is they are made with special concrete. They are what we really call a green structure, gray going to green. You can see these elements that were studied at the University of Miami, for dissipation of energy. But now I just want to give you an idea of what happened after just 6 months from the application of the um, structure for which we are looking at dissipation. So it has become an oasis of fish, and in only 6 months now you can see the population. So I think that with this I can go quickly to my conclusions. I think I've made a compelling argument, I believe, about sustainability and resilience. If we were to adopt where it makes sense, this technology, we can also save fresh water. We have major projects now looking at the use of seawater to replace fresh water in concrete, natural resources, including sea sand, recycle concrete aggregate, dune sand. We can eliminate corrosion. We can increase service life, obviously. And then the other thing that we can improve constructability by lowering the transportation and installation cost. Many thanks. Now is my turn to yield the floor to my distinguished colleague, Paolo Casadei.
Good afternoon, everyone. Thank you, Professor Nani. Thank you, Professor Pulido, and thank you, Yapsen Next, for today opportunity. I will start sharing my screen. I think you should see now. Please give me an okay.
Perfect.
So,
Perfect.
okay. So today's talk, I will talk about the use of GFRP, and in particular, I think the opportunity that we have, just to add to what Professor Nani just said, is really the opportunity here in Europe, thanks to the recent updates in the use of new certification methods to allow CE marking and new guidelines that are in development. Clearly, there is a different approach in design, even though it yields to the same result between European and US standards. And so this is important where we acknowledge that. First of all, very briefly, I'm a business developer for Owens Corning. Owens Corning is a Fortune 500 company. We started producing glass fibers, and we are now in the business of insulation, roofing, doors, and composites. Within composites, the business is really diversified, where in all the application where glass reinforcement is used between wind power, veils, and also clearly composite rebars. When we go into looking in composite rebars, it's a breakthrough innovation. Why? Because like Professor Nani described, we talked about glass fibers, ECR glass, and with a matrix of thermoset. And there is also now the opening to new type of resins, which allows the use of thermoplastic resins. At least those are allowed in Europe through the certification process, which we'll see why they could be very important. Pultrusion is the technology which mainly is used in manufacturing rebars. You see on the left the starting of the pools, then you go into the matrix, into a bath of resin, and then a dye, and then ultimately there is the cutting of the product. So the only limitation in this product is really the transportation issue. When we look into the shape, like Professor Nani said, there are different ways. The way the material works is you get the mechanical properties from how much fibers you can actually compact into a GFRP bars. And clearly the surface provides the bond. Here you see an image of a product which we believe performs really well in bond in terms of mechanical adhesion to the concrete, which is ribbed. And then you have the resin that really provides the protection to the fibers in terms of durability properties and also allows the composite action. There has been further development in the GFRP production by also looking at adding a lacquering that clearly provides a sort of like protection to any possible spikes of glass which can go out from the section of our GFRP bars. When we look into sizes, really we can look at size and nominal sizes just like we do for steel. What is important to know, that something that already was mentioned before, that when we look into band bars, we cannot think like we do with steel. And so we are limited in the types of shapes and curvature radius of our band bars. So it's very important then when a designers approach the use of GFRP bars, detailing and specification regarding band bars are really taken with attention, because clearly we cannot think in the same way we do with steel. But that is not a limitation, it's simply a new technology for which we really need to look and think differently. When we go into comparing the performance of steel and GFRP, and I think yesterday I had the opportunity and the honor to assist to a seminar looking at steel bars. Now, I think we don't need to look at ways to discriminate one product versus the other. Really is looking what product can give us an advantage versus the others. And among the other things that already were mentioned before, so I will not go more into that. I think what we really need to think, one of the advantages, apart durability, electromagnetism free, and all these other things, I think one of the aspects which really can drive the advantages in using GFRP is the fact the material is 4 times lighter. And that allows us really into lowering the impact that this material has on transportation as well as on handling. All the other advantages have been said already before, so I won't go into that. Another aspect that has been mentioned, but I think I want to put your attention on it, is really the sustainability and life cycle assessment, the better life cycle assessment that GFMP can provide. Not only we can reduce, we can basically zero the maintenance, but also we have great advantages by the higher durability properties. Also, we, like Professor Nani said, that there is a big potential already explored on new type of cements, looking into less additives into the concrete. We can certainly reduce the concrete cover because we don't have any more issues of durability. We only have issue of being able to transfer the bond stress between the bar and the concrete. And also, we have the big advantage of being able to recycle the material at the end as aggregate for new recycled concrete. There are also studies here in Europe by EU-CIA where the composites can become a way for for manufacturing less impact cement. So there is really an advantage in deploying the use of concrete with composite materials. And so basically here is just a synthesis, a summary of these advantages. Also, don't forget about the fact that safety first, and so also by adopting a material which is lighter, not only we have more sustainability coming from more truckload durability, but also we have a product that allows a safer environment in the construction world, in the construction job site, by the fact that can be carried by hand easier, so job site become faster and less injuries happens on the job site. Here, let me give you now some very brief added points. In terms of handling, cutting, and tying, we talked about handling, the fact the material is lighter. And so clearly, you can see here from the picture, there is an advantage in using this product on the job site. Cutting, it becomes much easier because with a normal blade, you can cut the material even in multiple size bars, no sparks, and no issue of safety. And as far as tying, really, the material can be tied in any traditional way. Can be used plastic ties, but also traditional ties. So really, the approach to the job site is much similar to the one that traditionally happens with steel. Clearly, the design is different, like Professor Nani mentioned, but we need to think about the rest as staying pretty much the same. Here you see kind of a overview, a zoom of the guy carrying 4 6 meters long 20 man bars. Clearly, that would be something not doable with traditional standard material like steel, black steel. Here you see a picture of the ties. Again, very similar to what is usually done with steel, no difference. Now, some just to give more voice to the application, here we can think about from going to the most complex application, but also the most traditional ones like dryways and slabs on grade, where again we take the advantage of reducing the concrete cover and of handling the material in a much easier way respect to standard steel. Here is a slab on grade. Again, you see the construction worker carry on many bars, easier to carry, easy to install, with a big advantage of not deteriorating and zero maintenance over time. Concrete repair issue, like we say, the advantage of installing reinforcement, reducing concrete cover, or in application in which concrete cover is already to the minimum, reinforcing the concrete section and being able to repair the concrete section in a more durable way. Here, application where they take advantage of the electromagnetic property of GFRP, the Metro Link of Miami, or elevated structural slabs in a parking garage. Application seawalls and decks, like already mentioned. And here I just want to show you some detailing of a concrete section where it has bent bars. Clearly, a concrete section like this one can be made either by closed stirrups or simply by taking two C shape, as you can see on the picture on the right, to prepare the foundation for a pier. Here is a canal, and I think I just wanted to, before going into the code, is really looking at this project that is also the background of our conversation today, which is Archer's Island Bridge in North Carolina. I want to thank Balfour Beatty, the contractor, for having passed the pictures. This is a project that is represent the first worldwide bridge ever built, fully reinforced with only FRP materials. GFRP were used for the foundation and the piles. As you can see here, some pictures. The advantages again of carrying material with lower cranes and easier for the contractor for the workers to place it. Whether FRP tendons were used in the pre-stressed beams that were supporting the deck. Here you see application realization of the bridge, of the foundations, the deck, the movement of the assembly of the rebars. Here again pictures. As you can see, again the tying of the bars is very similar to what it happens in a normal traditional reinforced concrete with steel section. And again, just few numbers: 65 kilometers of GFRP bars for the substructures, roughly 30 tons, 130 tons for the slab, with a total, and also 12 tons of bends. Now, if we really want to go into understanding one of the issues of this technology, more than on the straight bars, is really on the amount of bends. And that's really where we shall put our efforts to improve that. Now, let's go now very briefly in the code approved, how can we certify the mechanical properties of this material? One aspect that has been really important for this technology is delivering certifications, which have already been done in North America and Canada, like Professor Nani said, not only as compliance, but really in order to guarantee the mechanical properties over time. And that's what in the US has been done by ICCES in order to develop an acceptance criteria that not only certify the bars, but provide also compliance and assessment and verification of the constancy of performance. In Europe, this task has been deployed, I would say, recently by the development of the EAD, which is the European assessment document, which defines how carbon, glass, basalt, and aramid fibers bars can be used for application into concrete. Here you see a list of all the bars, of all the mechanical properties that has to be defined. And I think the most important thing for a producer, but really for the engineer that decide to adopt this material, that once the material is CE certified, there is an assessment and verification of concept of performance 1+, which means the highest level of verification and constancy of the product that could be adopted within the CE marking of a product, which guarantee that the material properties certified by the manufacturer will stay and will maintain throughout the production, thanks to a factory production control done at the beginning of the certification and issued yearly throughout production. And here you see on the right the pictures of the mechanical properties and the properties in general of the product that needs to be controlled and verified every year by the manufacturer, and also randomly verified by the technical assessment body that delivers the certification. Here you see some of the mechanical properties. Glass transition temperature has to be above 100 degrees, very similar. We clearly have tried to match some of the parameters, the compliance parameters that are present in the STM. The big difference that is really into that kind of characterize products certified according to the EAD versus the STM is how we determine the mechanical properties. By means that in the EAD, the manufacturer has to refer to the mechanical properties to their cross-sectional measured by Archimedes test, which means that in Europe, we are not going to have mechanical properties raised by referring to the nominal, but really referring only to the cross-sectional properties. So that's how an engineer approaching this design of this material is going to see slightly the difference depending on in which part of the world is approaching. Like Professor Nani said, there is a pull-out test. In the standard, there is also the opportunity of doing an eccentric pull-out test. Pull-out test also after conditioning the bars. And the other very important thing is that this test does provide a level of performance of the bar, but the values that needs to be adopted in the design shall not be taken specifically by this test, because with 5 times the diameter, clearly we only have a reference of the performance of the bar, but this value does not really enter into the design. Also, this is also another very important question regarding bend bars. Like we said before, one limitation of this technology is given by the fact that we cannot bend GFRP bars on site. GFRP bars has to be manufactured separately in the production, by production. Usually the radius of curvature of these bars is roughly 5 to 6 times the diameters. Clearly the manufacturer is allowed to provide a lower curvature radius of their bar as long as the minimum mechanical properties that are listed in the code meet the specification. Usually, the strength of bend has to be greater 50% of the straight of bends. There is an evident reduction in the performance of GFRP bars. And again, this is the limitation. It's not nothing bad, but we need to know these limits, these different performance in order to design more efficiently our concrete section. Another important thing, which again has to be known, but by knowing it, we simply need to understand that again, testing that we need to perform over our bars, provide us the necessary level of trust in the material. GFRP bars suffer alkali exposure. And somebody may say, well, boy, we're using it into concrete. Concrete is an alkali material. So how do we do? Well, we simply test and we demonstrate that after 3,000 hours, there is a reduction in our property less than a certain percent, and that is defined by the code. And that difference in this test allow us to aim designing for greater than 100 years design life of our structure. So yes, there is a limit, but yes, there are ways to go around that, meaning to demonstrate that the producer is capable of outperforming this test, and so no limitation are given to the material. Clearly, this is a very important test to perform. So when looking at the material, this is something that we need to look first more than the mechanical properties itself, because clearly we may have a very performing material, but for many reasons, pultrusion may not excel. And in that case, voids and capillarity may provide problems to the product. And so similar to what happens with any construction material, this is something very important for which we need to be aware. And this is just a picture, very briefly, of a mechanical property data sheets where you have the reference of the nominal diameter, the linear weight, the measured cross-sectional area, characteristics, short tensile strength, the load, the strain, the modulus elasticity, and also the fiber mass content, which is kind of give us really a flavor of how the mechanical properties are obtained, and then also all the other parameters which are important for again qualifying the product. With that said, I complete my presentation. I hope you appreciate again a vision over the use of GFRP, and I pass the word to Professor Kawamata, who will give us his talk. Thank you.
Thank you, Paolo. Thank you to Professor Pulido for the invitation, and also Yapse. And I'm going to show my presentation. Second. Yes. Okay, today, first of all, like was said, I'm a professor in Italy, at the University of Chieti Pescara, and I'm also technical director of Asdea, a company that mainly develops software and artificial intelligence for monitoring of infrastructures. And today I'm going to talk about two topics mainly. One, GFRP. So I'm going to show a couple of examples and ideas. Also, I saw a question regarding ductility of this material. So I want also to give an idea of how we can obtain also a ductile behavior with these materials, even though we know they are brittle. And I'm going to show also some applications of advanced numerical analysis to ensure the safety and capacity of this type of structures. And then I'm going to discuss about structural monitoring of this type of infrastructure to ensure the safety and the performance of the infrastructure in time. That's a very interesting and modern topic that is becoming more and more important in the infrastructure world. So first of all, a lot of the previous talks talk about the resistance of the material corrosion. It's corrosion resistant, it's lightweight, Professor Manni mentioned about it, is efficient in construction, and is sustainable because it's much lighter than steel. So the cost, one of the largest costs for the sustainability is transportation, and in this case, you can also save a lot of problems. So what is the drawback? And also this was the question. One of the drawbacks of GFRP is mainly the brittleness and the limited ductility. And this raises a lot of concerns among engineers in general, but particularly for in seismic zones, where you require a lot of dissipation. And so I'm going to show some examples of how we can also prevent this problem when you have a medium to high seismicity place. And you need also to combine this with different materials. So I'm also to show a reinforcement strategy where you can mix steel with GFRP, and you can maximize the efficiency, safety, but especially ductility of the section, and ensuring also the durability of this type of section. I start with an interesting test that a lot of people were involved with it. So I just want to mention Professor Fausto Mistretta, that was a designer. I was a consultant for the test setup and also for the numerical analysis. And Manini Prefabbricati was a builder. That's I think the largest test that was performed on this type of structure. So it's a beam 23 meters, bridge beam, pre-stress. And I'm going to show the idea that I think is quite innovating and interesting. But before I start with some simple tests made at the University of Cagliari. University of Cagliari started an extensive campaign to evaluate the shear strength of GFRP sections. So they perform several tests with only a GFRP cage. Like Paolo was mentioning, one of the most interesting topic, I think, for this material is evaluating the shear strength because of the bend, so the reduced strength of the bend. So it's a very interesting topic, and we are currently working on it. So you see, this is a cage, as I said, completely made of GFRP. And also the rebars, you can see the stirrups bend. That's a very, as I said, important issue. How we model it, we try to model also these beams with very advanced numerical models. In this case, we used also bond slip, because like Paolo mentioned, it's an important characteristic of the material. And we need also to model the bend, as I'm showing, to see what is the effect of the bond stress, but also the effect of the bend in the performance. And we use a sophisticated damage concrete plasticity to consider the behavior of concrete in tension and compression. You can see the behavior, the damage plastic behavior of compression at the top, and the tension behavior at the bottom. As you can see, we can model the plasticity and also the damage. That's the first result, and was a blind test. So, we wanted to evaluate if we were able to reproduce the shear strength of the material. It was a 3-point bending test. As I said, we performed several. As you can see, we can also model very accurately the bond slip and the loss of anchorage of the GFRP rebars and the shear failure. And as you can see, these models are able to reproduce quite well. So the experimental results, because we are, if you see the numerical is 90 and the experimental is 93, this gave us a lot of insights regarding the stresses on the rebars, and especially the stresses on the bed. It is, as we said, the most important thing to evaluate. And we obviously could consider also the strut in compression and see how the strut is behaving, to see if the typical model where you are using the modified stress field theory, so taking consideration of the truss with different orientation angles, if it works also with this kind of materials. That's the solution. Instead, with Manini, we tested, and a secure solution with the designer is very interesting, because the idea is to use the tendons for pre-stress at the center of the section. So in this case, you ensure 10 centimeters of concrete cover. So you have an extensive protection also for carbonation. And the external reinforcement is all made of GFRP. So think about the advantage. You have the same type of ductility for the pre-stress, but at the same time, way longer durability, because the GFRP is the external and only the steel is internal. I think it's a brilliant idea for bridges, bridge decks, and bridge girders. And even for slabs, sometimes could be very efficient. This is a picture of Manini, of the construction. You see, it's a huge beam. As I said, real scale. and nothing to say. As you can see, we have a very the distance between the stirrups is very short, but as you can see, also the band. Very interesting to notice how it is, because the band can guarantee a good bond. So this is a model that we developed. You see how it's very sophisticated, because as I said, we wanted to see also the behavior of the band to ensure that everything was working properly. And then we would check after the test the band strength. And in this case, also was interesting that Manini decided to go up to failure. And they asked us, we will see, to do first the blind predictions. So we had, without having the data, obviously the results, we had to predict the strength. We first perform a 4-point bending test of flexure, and we wanted to evaluate the stiffness of the beam and also the cracking pattern. And then later we performed 3 shear tests. I'm going to show one, and we evaluated the shear strength to 2,500 kilonewton. And we also considered that we also found out that probably the tendons were going to yield first. So we would have some ductility in the response, and then the shear failure, as you see, the diagonal shear failure. That was a response of the test in flexure. You see the numerical reproduced very, very well the test. And we are quite satisfied by the calibration of the model. And then that's very interesting, like I'm showing you the predicted failure and then the failure that we obtain on site. As you can see, the model reproduced perfectly the test. And we could evaluate also, as I said, the stresses on the band just before failure was way below the allowable strength of the band in the GFRP rebars. And the experimental failure was up to 2 tests. One was 2,400, the other 2,700. So the error was roughly 7%. So the models work very well to model this kind of structures. Another idea is a new hybrid concept where combines the steel reinforcement with GFRP. And this was studied for seismic region. I'm a seismic engineer. So I was also concerned about the ductility. And the idea is to use an internal cage of steel rebars. The steel rebars are perfectly connected, anchored to the foundation. So also you can think about a joint, or think about a bridge pier, where you have the internal cage, and you can guarantee 10, 12 centimeters of reinforcement, concrete cover reinforcement. And all the critical region is designed with the steel reinforcement and also the confinement. So we can ensure large ductility of the performance because it's only controlled by the steel structure. The external cage instead works only for static behavior. In particular, as is designed, the GFRP is not anchored to the foundation, so it's not working for seismic, it's only working for static load. So this will solve completely what is the problem of ductility, increasing the construction cost just not much, but ensuring a huge increase in the durability of the structure. And thinking, as I said, regarding, for example, bridge piers or columns of external structures. So this is a numerical model. I want to show you the results. So here you can see the internal cage fully anchored to the foundation, and the external cage GFRP not anchored. So we are not even concerned about the bond of this kind of rebars because we don't need to guarantee the bond, the perfect bond. We model everything, including the bond slip of the rebars, steel, and also GFRP, and obviously concrete behavior and GFRP elastic brittle behavior. Look at the results. Very interesting, I think. So you have the traditional, this is a cyclic behavior of the joint. As you can see, the traditional steel, we had an experimental values for this. This is database from Peer. And you can see the cyclic behavior. And these are the dotted lines. Instead, the black lines, they are the hybrid solution. The ductility is exactly the same. We obtain very similar results regarding also the concrete cover spalling, and also the buckling of the rebars is not much different because, as I told you, the GFRP rebars are not anchored, so they are not going to be highly stressed. You see the level of stress here on the left. You are about 200 megapascal, 300 megapascal, so way below what is the strength of the material itself. And the crack width is also contained. We are talking obviously about high ductility. So, you have 2 millimeters at the base, but this is expected because you are going to have rocking of the system. So I think it's very interesting. And now with Professor Nani and other professor, we are testing the solution. So we are very interested in seeing the results also from like experimental results of this solution. Another thing that I really believe is the fact that for infrastructures, and especially for new structures like this that we are analyzing, it's important to monitor the performance in time of the structures. And to do that, we have systems. In particular, we use sensors, or we'll see dynamic sensors for evaluating the frequencies and damage of the structures. And we use acquisition units also to evaluate also the static behavior. So with potentiometers, strain gauges to see the deflection, inclination, and also, as I told you, to calibrate the frequency. I'll show you an example directly of a bridge. That's a very important bridge in Italy. It's one of the, there are like 26,000 heavy vehicles daily on this bridge. It's 2 bridges of 160 meters. It's on the highway A4. We instrumented it with 900 channels. So we wanted to have really large information of the behavior of the bridge. And we are analyzing the bridge using artificial intelligence. In this case, I'm going to show you how we do it. But we also calibrated a digital twin. So we have a numerical model that is fully calibrated using artificial intelligence to the sensors. And we have also designed a data visualization to see the results from the web directly. So we use optimal sensor placement software using genetic algorithms to decide where to place the sensors. And we are using a data acquisition processing solution that is real-time, continuous. And we are using a quite not expensive solution because we are not using expensive cables of DAC system, but we are using just a computer with a normal Ethernet connection to evaluate the performance of the bridge. That's the result. And as I told you, for bridges made of GFRP, I think would be crucial. For the physical model, the physical result is a real bridge. So we are reading the data from the real bridge. We evaluate the frequency, and we synchronize the numerical model that is a full digital twin. So numerical model, finite element model of the bridge. As you can see, we can completely evaluate the frequency of the bridge in real time and with a very, very good definition. This means that the numerical model is fully calibrated with the physical. And we evaluate the behavior, the performance of the bridge using statistical data and artificial intelligence. So think about, we measure the performance of the bridge using a lot of different features. And then after 1 year, we detect that there are anomalies. It's like, just to give you an example, monitoring your heart rate during 1 year. And after 1 year, we can tell you if there is a different trend, if there are problems in your average heart rate, in your maximum heart rate, in your standard deviation. So if there is a problem with your heart rate, we can detect it, and we do the same with bridges. So in the case of GFRP bridges, it would be very interesting to see if there is damage or cracking is exceeding, if there are some issues with the new solution. This is a training period that normally lasts for 1 year. And this is anomaly detection. After 1 year, you start detecting the anomaly on the supports or whatever happens in the bridge. But what we like the most also for the GFRP is to be able to have a digital twin. So it's a completely synchronized model of the real structure. What can we do with it? We can do a lot of prediction. For example, we can run stochastic analysis, like in this case, of the traffic. And we can evaluate, we can predict what happens to the bridge in 10, 15 years. That's for a new material that GFRP is crucial because basically just with artificial intelligence and digital twinning, we can evaluate, for example, the fatigue behavior of the GFRP and evaluate what is the life expectancy of the bridge, or we can intervene. We need to intervene and how to intervene if there are some issues with the bridge. So the prognosis capability is very high because of digital twin integrated with artificial intelligence. And also what is interesting is the fact that we can also evaluate the performance, not only in service load, like what I was showing before, but also for extreme events. So we can run several earthquakes with different intensities and we can see the performance of the bridge, but the calibrated bridge, for an earthquake. And then we can train the digital twin with artificial intelligence, basically evaluate what is the damage just after an earthquake. That's really interesting. After a few seconds, we can tell you if the bridge has an issue because we have the data already calibrated with a digital twin. And this is an example of a post-event evaluation. So just after the event, we have the record at the base of the bridge, so we can evaluate the performance of the bridge right after the event. It's very interesting because, as I told you, for the first time, we have a calibrated bridge. So we have what we think is a real calibration and real behavior of the bridge in the numerical model. And this is a dashboard. In the dashboard, you have the information regarding each different sensor, static and dynamic. And you have also the information regarding the storage and also all the systems that are basically reading the information from the bridge. So you have the full control of the system. And also what you can do, also not only controlling the system, but you can even reprogram the system using changing the frequency of the acquisition or changing the acceleration, maximum acceleration, minimum acceleration. You have control from the office. You can have all the statistical data based on windows that are, can give you the trends of the bridge. Or you can use artificial intelligence in this case to evaluate the performance with the different anomalies that you can read and also elaborate. That's very important to see what is the anomaly. Or you can have the digital twin. So on the left, there is a physical, so the real bridge. And on the left, you have the numerical with all the sensors. So in this case, as I said, it's very important because you can use information from the numerical, in this case, the deformation of the bridge in real time, inclination, or we'll show you also the stresses of the bridge in real time. So just coming from the information of the data of the sensors. In this case, you have the modal analysis of the frequency. And at the end, you can also have a view of the beam with the information regarding the sensors, with all the information regarding the sensors, so installation, maintenance, and every information you need for the sensor. So thank you very much. I think I'm 1 minute ahead of time, so strange for an Italian. We normally spend a long time, much longer. So I'm going to give the microphone to Pedran Monocheri. So please, you can share your screen.
Thank you very much. And thank you, Professor Polido, for the invite and the UPSE. If you please confirm that you see my screen.
Yeah, perfectly.
Very well. I will be speaking about a specific application of this material, FRP materials. And this case is a rehabilitation of a historical bridge. This is Udondo Bridge, which is in Bilbao, north of Spain. Okay, the story of our bridge starts in 1844. This is called Isabel II Bridge, and this is the bridge that part of it will be reused in a new bridge. The bridge was designed and constructed in 1844, as I said, and it was in service until 1874. This type of bridge also important because this is one of the last remaining of a bridge, historical bridges called Polonceau bridges after French engineer Antoine Remy Polonceau. Please excuse my French. The Isabel II bridge, or Arenal Bridge, as it was called later, was destroyed, was damaged during war, and it was destroyed by flood a little bit after. In the figure on the left side, you can see the bridge that it is still in service, but the spans are replaced by wooden struts. And on the right side, the bridge is almost destroyed. This is right before demolition of the bridge. But you still can see some of the arches, which are cast iron arches, and one of the very good examples of this kind of arches are still intact on the right spans. So if I go to next, so an engineer named Pascal Landa, he had this initiative to recover these pieces and build a new one on one of the tributary of this, say, the same river. So 6 of the arches were recovered and installed then in 1876. So the same arches reused in a new bridge. This bridge stands until today. This is a view of this bridge, and you can see on the right side that the arches are now covered under a deck of concrete. This was done in 80s or 70s. The bridge is still in use, and on the figure below, you can see that it was extended by concrete elements, and these pieces are the old arches. So the bridge is quite old, and it lasted far beyond the design life of service life of any bridge. So you can see that this is the situation is getting worse, and the city of Bilbao decided to start rehabilitation process of the bridge. So one restriction that the bridge has, the design has, the rehabilitation design has, is keeping this space above the arch. So there shouldn't be any interference with the old structure. So to do this, we can use many solutions. On the right side, you can see that these steel elements are added, but this wasn't the best design that we liked, and the disadvantage of it was that this is also a heavy design and heavy elements, and adding it to the old masonry walls, abutments of the bridge is adding some weight to it. And also, it is a little bit crowded, and too many elements will be sitting in this very small gap. So, what is the better element to use here? What is a better design to do? What is a better material which is lighter, takes less space, and it can replace the load-bearing part of the structure? So the answer was, at least in this case, was kind of FRP solution called hand laminated U-shaped deck. As you see in the figure below, the space remains after the installation of these elements. So the concrete cover on top will be removed, and this element will be replaced. And the advantage is the higher strength of these fiber reinforced polymers. On the right side, you can see that there are other examples of the process of developing this hand laminated composite decks. Earlier examples of this, as far as I could find it, it was first done by Lockheed Martin in 90s. They built a test bridge with this U-shaped girders, and it was also continued in 1997 for Smith Road Bridge in USA. I'm going to jump to a newer implementation of this design. These are bridges built in Madrid in 2004, developed by Acciona Research and Development Group, and these are highway bridges. So this is a very good example of this applicability of this kind of design. So we did use the same, more or less the same design, same approach. And okay, now, by the way, we will get to the FRP rebars too. So this is the process of that we are going to follow. This is the old design, the old bridge. First micropiles will be installed, and then the abutments will be installed in a way that this is not intrusive, and it doesn't add a structural and construction load to the old structure. The concrete deck that was installed in 70s or 80s, it will be completely removed. At this stage, the arches could be dismantled and sent to the to be tested, or for the situation of them to get improved. They can be fixed, and then they can come back to the bridge, and the bridge will be active until it is finished. So the final view, final aesthetic of the bridge will be the same. So on the right side, you can see the final bridge. Nothing visible, everything is the same. And the new solution will be hidden inside the old design. Very well. Now let's talk very quickly about the cross section of this. This is composite section with glass and carbon fiber on the bottom. Carbon fiber is only used at the bottom section because of its higher modulus of elasticity. It controls better the displacement, the deflection of the deck, and also it reduced the final cost of the product. And one thing that is completely new in this design is that the studs, the connecting studs, are installed inward, and part of this section is filled with concrete. So this is how it is done. This is to increase the stiffness of the deck, which is integrated to the top slab. The concrete is filled in this first part of it, which is supported by a normal elastomeric bearing. As for rebars, using FRP rebars, glass fiber rebars, everything is glass fiber in this case, because with that we could reduce the concrete cover, which was due to Eurocode instructed for this to be higher. It's the number is so large that is making the the slab much thicker. And with this, we have reduced the thickness, and actually we have a much lighter design. The slab is lighter and more slim. So everything is done with, every reinforcement is done with GFRPs. Well, I guess I close with this. So we have used this U-shape design to minimize the deck thickness and reduce the visual impact. So this historical heritage will look always the same. The GFRP rebars are resistant to the corrosion, and because this is located in near sea, and therefore we have a slimmer deck. And Pascal Landa has this idea, this initiative to save this historical arches and use it here. This cast iron material were quite advanced material back in the time. And now, with the help of new materials, with these innovative materials, we are going to save this and continue this spread and save this for the city of Bilbao. I should mention that the project is still not finished. That's why we didn't have pictures of it. But we hope that this is going to be done soon. Thank you. I finish with that.
So thank you, Pedro. I'd like to thank all panelists today for this interesting webinar, for the presentation. We have, as indicated, a Q&A box in the Zoom platform, which we'd like to use. I have a number of questions there, and I'll begin to discuss now in the order in which they have been asked, but please feel free to type any other question which you may have. We have some time left now, so let's capitalize on this expert to ask questions you are interested in. The first question, I apologize for my pronunciation with some names. A question from Jim Shinkia. How, of course, some questions are addressed to some specific panelists, but if I don't say any specific name, feel free to answer whoever you want to. How do we address the brittle failure issue of the GFRP and the fire resistance of the FRP?
Can I take it?
Okay.
Okay, so excellent questions. The brittle nature, we recognize the fact that this material is linear elastic to failure, but I think that Professor Kamata gave you a good idea on how you solve this issue in seismic regions. We do not advocate that there is a dissipation of energy, obviously, but if you remove from the seismic the same level of safety that you have in a situation where you use a reinforced concrete with the steel rebars, you can get it with the GFRP bars if you look at the deformability rather than the ductility. And deformability means nothing more than the curvature, let's say, of a flexural, or the cross-section of a flexural element is such that the strain in the reinforcement exceeds, for example, according to the US code, the 5,000 microstrain. So for the brittleness, and in particular brittleness in non-seismic zones, there is absolutely no issue. You also raised the other question, very interesting, fire. For the time being, we have, again, I refer to the 440.11, we have indicated that if you have questions related to fire performance, let's say a 2-hour resistance, you have to provide it with other means. There is a lot of research now underway to indicate that provided that the FRP is properly anchored, the fire resistance may be even superior to that of a steel RC. And the reason is because the fire would degrade the resin. I believe that, actually, I'm sure that Dr. Casadei mentioned that the TG of 100 is when the resin seems to be reaching a point of no return, but the fibers are not compromised. So provided that you have the bond in regions that are not affected by the fire, you're okay. So there is ways to address both issue, the brittleness and the fire, but these are certainly very important items that are in the eyes of all of us. Thank you for the question.
Okay, thank you, Professor Rani. Another question from Jean Sinkia. Since the GFRP cannot be bent on site, how do we do reinforcement or rectification work which involve exposing the reinforcement and rebending them to the required shape?
If you want, I can take this one.
Yes.
I think we need, like I said in my presentation, we need to consider the material differently, meaning we need to start thinking on taking advantage of overlapping bend shape bars with straight bars, which means in the case of a refurbishment or even anchoring straight bars that we usually tend to do with an L shape at the very end, in this case, we need to start thinking on having straight bars with an overlap with a bend shape. And in the case of refurbishment or repair of an existing cross section, we may think on going with deformed bars that are already manufactured on site in predetermined ways, and simply really it's easier to go with an overlap between the straight portion of the bar and the bent ones.
Okay, thank you, Paolo. Another question from Lincoln Wisvast. Indian code use of a steel rebar and GFRP bar is restricted. In a slab for cherry steel rebar is required. Please provide more insight in this topic. Yeah.
This is a difficult question, which I'm not
Yeah.
really fully understand. So but my understanding of the situation in India is that that country in particular is very interested now in the use of GFRP. One of the reasons is because of the lack of aggregates. The issues related to excavation of aggregates has created many hydrological problems in the country. So the idea of using aggregates outside the riverbeds or quarries seem to be indicating that you can use composites, so you avoid the issue of corrosion when you use, let's say, for example, sea sand or sea aggregate. I don't know if the question is, can we use GFRP and steel in the same cross section? You could, but I don't think any code will allow you at this time. We're working on it actually on the Italian CNR 203 code, as indicated by Professor Kamata. There is many reasons to consider the combination of the two reinforcements, but if that was the question, I don't think that there is a permission now to do it.
Thank you, Professor Nani. This question is addressed to Paolo Casadei from Fini Ambika. A specification for lapping of cages for peeling work.
Yeah, well, the overlap is in that case depends on the size of the bar and on the bonded requirements in that specific application. Usually, there is a reminder on which we are now working, like Professor Lani said, in the Italian guidelines at the European level. There is a reference of around 40 diameters, so you would need to have an overlap depending on the size of the diameter of the bar of roughly 40 diameters, similarly to steel. So any better performance shall be obtained by really looking at the bonded length and at the stress at which that bar is working in that specific condition. So reducing the stress, clearly you can have lower bonded length. But if you are in a design by which that specific element has at the highest level of stress, then clearly you need to go with the highest bonded length.
Thank you, Paolo. Another question addressed to Paolo as well from Nicolas Sandoval Montoya. In the EAD bonding test, how can we use the bond strength obtained and the reduction in bonding strength between the centric and eccentric tests in the Eurocode?
That's $1 million question. Because honestly, there is no correlation. So this is one of the things that sometimes we do, and then once we've done it, we realize that probably we should have done it differently. And again, that now depends on the industry which has defined the testing. The only added remark that I would make is currently the Eurocode, the Annex R of the Eurocode is very conservative. Have a very conservative approach because it sums up many coefficients into the reduction of the performance of the bars. Right now, there is no real correlation between the bond test by pull-out and the bond performance bond equation which is in the code. So like I said, or like I tried to say, the bond test, which actually in the EID has to be done on a concrete that has only 20-25 concrete strength, so it's very low. It's more to be looked, and again, the Eurocode does not refer on that. That's something we're working on other guidelines, is more as a sort of like a pass, no pass type of thing, meaning you do the test, you reach a certain load, certain stress. If that stress is above a number that, for example, in ASTM is defined as 7.6, then megapascal, then you can adopt the bond equation which are in the code. But there is no direct correlation between a higher load of a bar respect to another, as long as they pass the 7.6 value or the 9 of the new STM.
Thank you, Pablo. You are very popular. Next question is asked to you as well. What does the type of NDT test aim to detect in the future for existing structures? Is an anonymous attendee.
What does the type of non-destructive testing aim
in the future for existing structures?
Oh, I don't really know what it means.
Maybe I can help a little
go.
bit. This is a very important question. You know, the traditional methods to identify rebars, steel rebars in the concrete structures do not work with FRP. There is a lot of research, actually some funded by NEX, to develop NDT techniques to identify the location of the rebars. Why is this very important for the bridge community? Is because, for example, if you have to core a slab, you need to know where the reinforcement is before you start coring. So excellent question, difficult answer for the time being. There is companies that are working on this, in particular one coming out of Europe, Switzerland, and Screen Eagle. So if you want the name, but we are attempting to also address that very important issue, detecting location of bars and size of bars that are embedded in concrete.
Thank you, Professor Nani. Feel free to answer whoever you want to these questions. From Samer Sawant is a proposal of research line. Can we attend for a FRP rebar with a steel embedment and helicoidal to improve ductility? Example, say a 16 millimeter diameter FRP bar with 1.6 millimeter steel embedded in the central core of the FRP bar. Also try, there are many ideas using rebar stereo. The idea is like a reinforced concrete column with reinforcement on a steel rod, but for a single FRP bar. So
maybe I can also take this, if you don't mind, this idea of hybrid in the sense of hybrid bars, not hybrid reinforcement, has been tested in the 90s. Actually, when I was in Japan, I remember we developed a system, but it's really hard. People have also tried combining different types of fibers, for example, carbon and glass. I think that advantages, the potential advantages that are on paper are very difficult to realize. So imagine what happens when you're stealing the core of the bar yields and the FRP continues working. It's a neat idea that attempts to solve the problem, but creates many others. So I think from an R&D perspective, this has not found a follow-up.
Thank you, Professor Camara. A question from Enrique Hernandez Montes. Can GFRP bars be used with regular reinforcing bars, overlapping them? Are there experimental tests on this topic? Who wants to answer? So overlapping two different materials in every bar.
Okay, I can take this again. I think it's potentially similar to a previous question. Yeah. We do it regularly in applications in the geotechnical arena. If you think of a soft eye, where the GFRP is using the core of the wall and the steel cages continue around it, you are really splicing GFRP and steel very effectively. But if you ask, is this done in conventional, let's say, girders or columns? I don't think we have any experience with that. But in walls for, geotechnical application, this is done regularly.
Thank you, Professor Nani. Another question for Asterios Balogiannis. When you speak about the durability of the GFRP bars, and especially their use in harsh and aggressive environments, do you also take into account the durability of the polymer, epoxy or vinyl ester resin?
Yeah, if you want, I can take this one. Yes, because the test on the bars is done by immersion of the full bar as it is into an alkali bath at 60 degrees. And so because resin clearly provide the composite action between the filaments of glass fibers or any other type of fibers, you are testing the full composite action between fibers and resin. This is tested not only in tensile strength, but also in interlaminar shear, which is really the test that kind of gives you the behavior of the composite action after conditioning. And so the retained mechanical properties take into account degradation of the full system. The resin, which in a sense is the one that goes first because the one on the round, and also if the fibers are attacked, you will see clearly a lowering of the mechanical properties. So yes, the answer is yes, you take it into account both products which are composing the bar.
Thank you, Pablo Quesade. Another question from Christian Londono. Considering that the seismic design in Latin American countries speak about R factors rather than ductility and even rather than displacement capacity, how can we find comparable factors or methods to relate them? Yeah, it's similar. So
maybe I can answer to this one. So
yes, you should.
So the R factor is a different perspective, but as the same, basically comes from the same family. So you're reducing the demand based on the ductility of certain structures. So you look at the forces, you are not looking at displacement. And this is typical for linear elastic analysis. So we have been looking already at the R factor in Europe. We call it Q factor. Anyway, for only GFRP, we are suggesting a limited ductility or essential elastic behavior. So you are thinking about the Q factor, R factor equal to 1.5 maximum. And if you use an hybrid solution, you can, and this is what we can prove, we want to prove in the future, you can use the same R factor of the steel structure. So you can use the same exact approach. You just have to define correctly the R factors.
And then if I could add to it, and I totally agree with what my colleague, Professor Kamata, said, in the United States, this issue is a little bit difficult for us because it's not a prerogative of ACI to establish the R factor, we look at ASCE and BCC. So is the ASCE that through a document ASCE 7 gives us the values of the R factor. So it becomes a much broader type of conversation, but I think the explanation of Professor Kamata gets to the issue of the science and why these values are so important. I think it's to us, the research community, to come up with the evidence that justify values also for GFRP reinforced structures.
Thank you, Professor Nani and Kamara. Question from YouTube. I didn't know that they were watching from there. From Jatin Singla. Can we compromise with the cover to GFRP bar?
Compromise?
Yeah.
What was the meaning? Like reduce the...
I'm not sure, but it's clear with the work that you have presented project that is, can we compromise with the cover? I'm not.
I mean, for sure you can reduce the concrete cover with the GFRP. So because you don't need, the only concrete cover you need to guarantee is to avoid cracking due to the expansion or thermal expansion of the rebars, but you don't need to provide like concrete cover because of durability. So it's a big advantage.
Oh, we just did in this project, so I hope that is fine.
I have another question, the last one from Samer Sawan, proposing another hybrid design. I don't know if you, because I think you say the answer before. Maybe we can replace the steel embedment with a carbon fiber bar and the liquid aileron bar. Will that worth trying, as carbon fiber are expensive than glass?
Carbon fiber are way more expensive than glass, so these are big issues for construction for sure. So theoretical, they are really interesting to use, but
and there is another major issue. I totally agree about the cost that is more than tenfold, but there is another issue that is the supply. There would be not enough carbon for a single bridge, let alone just going, replacing significant amount of FRP. So I think the answer to this question is, for the time being, unless technology changes and the methodology of making carbon fibers drives down the cost and increases the productivity, I'm afraid that carbon will be limited to repair rehabilitation, where is really the key material. But for internal reinforcement in new structures, I seriously doubt that in the near future we will see any development.
Yes, so there are no more questions. So
I have one, if I may.
Sure.
For Professor Nani. So
sure. Sorry, Pedro.
how, I don't know if it's okay for panelists to ask questions.
Sure.
How long do you think our rehabilitation lasts? Can we hit 100 more years or no?
Wow, you want to name me with this question. Okay, so actually, again, another very important question. I can only speak to our experience in the US. It all depends on the requirements of the owner, of the customer. Some repairs are done for a short time because you really need, for example, in the case of some bridges, you need to extend the life so many years before the bridges are demolished, not because of life safety, it's because of serviceability. So, for example, you have a bridge that does not have sufficient width to allow, the enlargement of the lanes or having, sidewalks or whatever. So you repair it for 5 years with the idea that 5 years from now. So I think that to answer the question that you pose, if the client were to be interested in long-term durability of the repair, the answer, more than coming from me, comes from a colleague like Professor Kamata that says you have to monitor it. There is no way that upfront, you can predict what the life is. The only thing that I think you have done properly, make sure that if you are repairing from the outside, that you have the materials that are on the inside are not corroding and so on and so forth. So it's a very complex question. And I think, the only thing is like anything in life, you have to look at it, monitor it, and you might be surprised by the length of life, which obviously will overlast me without any doubt. But excellent question.
Very well, thank you.
So, well, I really enjoyed this webinar. It was fantastic. And finally, I would like to thank the panelists for their generosity in sharing their knowledge, for the effort in preparing this webinar, for the time, to thank so many online attendees for the participation and interest in the webinar, and of course to IAPSE for making possible and facilitating this type of event, which is having such a good result. So have a nice rest of the week, and bye. Bye.
Thank you.
Bye bye. Thank you.
Thank you.
Goodbye.
Bye-bye.
Thank you.